Now that we have done the work to figure out what constitutes a basis of a vector space, let's look at some geometric examples. First of all, to recall the criterion, what we had was the following. There is firstly an obvious condition about covering everything, which I won't bother to state. Let's take it that we verify in each case. But the other one was something which was stated for finitely many sets, but in fact by induction we need it for only two sets. V W belongs to B implies that for all x in the intersection of V and W, maybe I'll be consistent in notation with the previous time. So let's call these V1, V2 in B. For all x in V1 intersection V2, there exists W in B such that x belongs to W and W is contained in V1 intersection V2. Okay, so this is all we have to verify, plus the union condition, as I said. So this will let us get lots of examples. Okay, so for example, if I draw a few circles, so example, first of all we have an open disk. Why is this? What is it we have to verify? Well, suppose this is the first open disk, and I take a second open disk which intersects it. If it doesn't intersect at all, nothing to verify. Then given any point in it, maybe it's somewhere here, it may not be in the middle at all, we can find yet another open disk, and now it's maybe becoming a bit small to draw here. Let's redraw the point, which was actually a circle by mistake. So if I'm given a point here in red, this is the one which I have to, and so this is the point x in the intersection. Then I can draw an open disk which maybe this, I'll draw it a little thinner in this color. So if I manage it correctly, I can draw an open disk here, and this is W. Okay, so let's label things now in these disks. So this point here, the red point, is x, and we have V1 and we have V2, and this one is W. The purple circle is W. So given two open disks, I can find something which is, and a point in it, I can find a disk which is contained in the intersection. So open disks, they form a basis. I have to insist on open because on the boundary it's problematic. You won't necessarily find these. So they form a basis. Okay. For a topology on R2. Here's a second example. Similarly, well, instead of saying sudo, let me just say it here, open rectangles. I could also take open squares, I could take diamonds, I could take lots of things, but let's say open rectangles with, or in fact I can specifically look at just open rectangles parallel to axis. Once more, this is because if I took two open rectangles which were parallel to the axis, and I had one of them which was this black one here, and then I had another one which was this blue one here, and I took any point in it, then I can find a rectangle. This time it's a little easier, parallel to the axis, which is contained in both of them. Okay, so yet again, not a rectangle. This one is V1, this one is V2, this is the point x, and this is W. We can find a W which has these. Okay, so in fact, so remark, and we can it's a puzzle to figure out the general condition. These give the same topology. And I'll tell you the reason in a picture, as if I'm given a circle and I'm given a point in it, maybe off center, then I can find a rectangle which contains that point and is contained in the circle. And conversely, I could do it in this picture itself, but it will become too small if I am given a rectangle and I am given a point wherever I want in it, as long as it's an open rectangle. I can find a circle, maybe this was blue, which contains this point, okay, and is contained inside the rectangle. So you can put rectangles in circles containing a point, circles in rectangles. You can, it's an exercise to formulate this as a precise statement not involving pictures and to prove this. Okay, so I will leave that aside. But let's look at a couple of other examples and non-examples. Okay, so here's another example. We look at only vertical strips. So this is still in R2, so infinite vertical strips. Okay, so that is to say, let's take, my lines are not going to be infinite, but I'm going to have the region here. And of course I should clarify open vertical strips. So I do not include the boundaries, but I include the entire region inside any such strip. I can take any thickness and take it anywhere. Okay, and the reason they form a basis is if the two of them intersect, which will happen if I take a line like this, and for example this way, and this is also a vertical strip, and I take a point here. This is just like an interval. Okay, my picture has become such that I could not actually picture has become such that I cannot actually draw vertical strip fitting here, but you can see that there is a vertical strip contained in this, just like an interval. Okay, so this is an example, and let's look at a non-example which is similar. So this is the example, and here is a non-example which is infinite open vertical and horizontal strips. If you want as a variant, you can think of strips in all angles also. And then the reason for this is clear, because if I take a vertical strip here, which is going to be black as before, and I take a horizontal strip, okay, these two were not quite parallel, but let's pretend they are, and I take a red point, which is not a strip but a point here. Okay, so now this, since this is positive, let me spell out, this is my set V1, this is my set V2. Now this region here is V1 intersection V2. Okay, and so if I'm looking at B consisting of infinite open vertical and horizontal strips, I must have W, which is either a vertical strip or a horizontal strip which is contained in V1 intersection V2 and contains this point, but that's impossible. So this is a non-example. We'll see the next video about subbasis, and in fact this will be a subbasis. Okay, and our final example is a bit again, so this time we'll turn to a slightly different set, perhaps on a fresh page. Let's look at X being R union 2 points. I'll call them minus infinity and infinity. Okay, so in this case, what is I'll take B to be the having various kinds of sets. AB, of course, AB in R, A is less than B. So let's have our line sitting here, and it's an infinite, but way out there you imagine there's a plus infinity, and way out here a minus infinity, and our first kind of open sets are intervals. Okay, but we also want to allow sets in things corresponding to infinity and minus infinity, so we'll allow union we'll allow a union with sets of the form A R. So let me just write it here, and then I'll explain what they are. It has to be open at A, so it's a mistake there. So open at A and closed at plus infinity A in R, and another class of sets which I will again spill out, closed at minus infinity open at A in R. And since I have written things this way, where A comma plus infinity is going to be the point infinity and the set of all x in R such that x is greater than A. Yeah, which presumably all of you would have guessed. It's a set which contains everything from here onwards and also the point infinity. And the other one is very similar. It goes off in this direction. Now, how do we know this is a basis? If we want to intersect, we have different classes of intersections. When we intersect two intervals, it's just like we did with real numbers. If we intersect an infinite guy with a finite one like this, and it's non-empty, we'll get a finite interval. If I intersect two infinite ones going in the same direction, that is two plus infinity ones, two of this kind of things, then I'll get an interval going off to plus infinity. And so given any, so in fact in this case intersection of basis elements is actually a basis element, not just a union of basis elements. Okay, so this is a real line with 2 points added at infinity and minus infinity, so that going to infinity means becoming large and positive, going to minus infinity means becoming small and positive. This will all be made precise as we get to convergence. So these were some examples where the basis lets you construct things. We saw an example where it doesn't, and so we will look at a more general concept called a subbasis, which helps in handling that kind of case where we sort of have different directions.